Okay. Now, hello guys. Hello. Good evening, everyone. How are you, everyone? I hope everyone is doing great. Now, in this class, let's discuss about the nerve physiology. So, the basics. Okay. Now, in this class, let's discuss about the basics in the nerve physiology. In yesterday's class, what I have explained you, I have explained you about the different types of neurons, how one actually feels the senses. Okay. Now, in this class, I will discuss about resting membrane potential. Okay, now I will be explaining about the resting membrane potential, and also I will be explaining about the action potential, the resting membrane potential and action potential, the topics which you need to know for your exams. Okay, now having said that, without any further late, now let's begin with the topic of resting membrane potential. Okay, so what exactly is this resting membrane potential? So you need to understand. So it's not just, this is not just for the neuron, for every cell, sir. For every cell, I'm telling you. Okay. What exactly is this resting membrane potential? See, resting membrane potential means, look. Now imagine this is one cell, sir. Okay. Now this is one cell. Okay. Now inside the cell, we are having what? Cytoplasm. Cytoplasm. Outside the cell, what do we have? We have the extracellular fluid. So this is the cytoplasm is nothing but the intracellular fluid, ICF, intracellular fluid head. And outside the cell, what do we have? Extracellular fluid. Okay, ICF as well as ECF, right? Now, so there is a, now you take a voltmeter. So now you take a voltmeter. Okay, now with the help of this voltmeter, now imagine this is a voltmeter. It is going to show the reading. Now you are measuring the voltage difference. Okay, you are measuring the voltage difference across the cell membrane. When you measure the voltage difference across the cell membrane, this voltage difference is called as resting membrane potential. Okay, resting membrane potential, what exactly it is? It is the voltage difference across, okay, voltage difference across the cell membrane. Okay, now actually, sir, outside the cell there will be more positivity, sir. Outside the cell membrane there is more positivity. Now inside the cell membrane there is more negativity, sir. Outside the cell membrane there is more positivity, inside the cell membrane there is more negativity. So the difference in the voltage is called as resting membrane potential. Now my question to you, why there is this difference, sir? Why there is more electronegativity inside the cell when compared to the outside positivity? Okay, there is this difference. No, this difference is called as resting membrane potential. For example, for this cell, I am telling the resting membrane potential is, for example, minus 60 millivolts. Okay, so why this difference minus 60 when compared to outside? Inside it is minus 60 millivolts. Minus negativity is there. Question is why? So now question, right? Why there is voltage difference? Because let me tell you one thing. In your first year, you should know, sir, imagine this is one cell. Okay, the same cell I am taking. Okay. So the composition, okay, nature have made our cells and tissues in such a way. For example, this is very interesting, sir. In your first year, you should know this. Where life have originated, you have studied in your class 10th, 11th, and 12th. You have studied that life have originated, life. Okay, life have originated in the seas. Okay, the seas, the first life have originated. Now the cells have originated in the seas. Now a cell have developed in a saline environment. In a sea environment, the cells have developed. They have developed all the processes in a cellular environment. Okay, so that's why even in our body also, our cells are there. No, they would love to have a sea kind of environment around them. So this extracellular fluid, whatever will be there outside the cell, ECF. The ECF is more like a ocean. The ocean environment, the sea environment is going to be there. in the extracellular fluid. What does I mean by ocean like? The composition, sir. The composition of the extracellular fluid, it resembles. See, now, if you ask me, sir, how you are saying this? देखो, guys, sir, outside the cell, in this extracellular fluid, there is more sodium. Seas are what? Seas are full of sodium and chloride. Okay, there is more sodium. There is more chloride outside the cell. And there is more calcium outside the cell. So, outside the cell, there are different types of ions present. Like outside the cell, sodium is more, chloride is more, and calcium is more outside the cell. But if you look inside the cell, okay, so there is more potassium. Potassium is more inside the cell. And even proteins, like anionic proteins, anionic proteins means negative charge proteins, are more inside the cell. So what I'm trying to put into your mind is, sir, there is biologically basic thing is there is a difference in ion composition. Difference in composition of ions across the cell membrane. This is the one reason. Okay. Next, the reason number two I will tell you. Sir, your membranes are made in such a way, our biological membranes are made in such a way, they are permeable to certain ions. Our membrane, cell membrane, it is selectively permeable. Okay. Selectively permeable. It is selectively permeable to certain ions. Means it allows certain ions to move across the cell. It doesn't allow certain ions to move across the cell. Means selectively permeable. I will give you an example, you will understand. Okay. Now, there you go, guys. Look here. This is your cell. Now, I have explained you, sir, inside the cell, who is more? More potassium will be there. Okay, intracellularly, the potassium concentration is more, sir. More potassium will be there inside the cell. Outside the cell, potassium is less. There is less potassium outside the cell. Okay, you know it. In this diagram also I have explained you. So potassium is more inside the cell. Outside the cell, the potassium concentration is very, very less. Okay. Now, sir, usually these cells, our cells, they have this channels, sir. Okay. Our cells, they are having certain channels. These channels are called as, look, these channels, what they are called as, I will tell you. These channels, what they are doing? Sir, according to concentration gradient, outside the cells, less potassium is there. Inside the cell, there is more potassium, sir. So, potassium is having concentration gradient, right? So, now the potassium, it can go out of the cell. So, from inside the cell, potassium is going out. Potassium is going out. As the positive ions, see, so the cells are having these channels. These channels are called as leaky potassium channels. These are called as the leaky potassium channels. Now tell me what these leaky potassium channels are doing. The leaky potassium channels are allowing the potassium to go out of the cell. Now positive charges are going out of the cell. As the positive charges are going out of the cell, tell me, sir, positivity is lost, like losing out. The positivity is going out of the cell. As the positivity is going out of the cell will become more negative inside. Okay, the cell will become more negative when compared to the outside. When compared to the outside, more positivity is going out. So the cell is losing the positive charges. So inside the cell, there will be development of negative resting membrane potential. During simple cell is resting, sir, simply resting. Okay. So because of this leaky sodium channels, sorry, because of the leaky potassium channels, there is development of resting membrane potential. Okay. Next, third thing, let me tell you. Look here. The reason number three is So these cells are having. Now try to understand. So this is a cell. Okay. So here is a cell. Now on the surface of the cell, so there is an important protein present. Okay, there is an important protein present. Do you know what is the name of this protein? So this protein brings by using ATP. Okay, by using ATP, it brings two potassium ions into the cell and is throwing out three sodium ions out of the cell. Okay, by using the ATP. Why ATP is being used? You already know, sir. Already inside the cell there is more potassium. Already inside the cell there is a lot of potassium. Okay, so now outside the cell there is less potassium. Now tell me, potassium is moving against the concentration gradient. Potassium is moving from less concentration to high concentration. Potassium is moving from less concentration outside to high concentration. So you need to use energy. So that's why ATP is getting involved. Okay. So what is the name of this transporter? The name of this transporter is sodium, potassium, ATPase. Okay, sodium, potassium, ATPase. Okay. Now, sir, what the sodium, potassium, ATPase is doing? You just look. Okay, you just look, sir. So, sodium, potassium, ATPase pumps, they are bringing two positive charges into the cell. Two positive charges are coming into the cell. In an exchange for what? In an exchange for three sodium ions. Means three positive ions are going out of the cell. But only two positive ions are coming into the cell. Means more loss of positivity. More loss of positivity. Okay, so these pumps will also contribute for the voltage difference across the cells. They will also contribute for the voltage difference across the cells. Why? Because more positive ions are going out of the cell and less positive ions are coming into the cells. Three sodium is going out, but only two potassium is coming in. So they will also contribute for the development of resting membrane potentials. Okay, so one is because of the sodium potassium ATPase. The sodium potassium ATPases, they will contribute to 5%, just 5% in the development of resting membrane potential. They will contribute just only 5%, sir. But majority is due to this leaky channels. Okay, due to this leaky channels. Now potassium is leaking out of the cell. Positive charges are going out of the cell. So cell will become like cell will get this negative resting membrane potential. Okay. Next, basically, okay, the cells are made in such a way that there is a difference in the ion composition. Okay. Now, why there is difference in this ion composition? I have to explain you why the ionic composition is a difference. Is a difference in extracellular component and in intracellular component. Why it is a different? Normally, what physics explains us. Physics explains us, and the chemistry also we have studied. Sir, substances will move from high concentration to low concentration. Usually substances will move from high concentration to low concentration. So equilibrium will be attained. Equilibrium will be attained. Now you know that, right? Now look here, sir. You are saying sodium concentration is more outside the cell. Chloride concentration is more outside the cell. Calcium concentration is more outside the cell. But why they are not coming into the cell? Maintaining an equilibrium. Why it's not getting maintained? Because let me tell you, there is something called as Denon's effect. Okay, Denon's effect. Okay, so what exactly is this Denon's effect, sir? Okay, Denon's effect, it explains us when there is an impermeable substance, large impermeable substance in a cell. For example, let me show you. Sir, I am taking. Dekho, sir. Now I am taking one cell, or for example, let's take one beaker as an example. Beaker. Now here I am keeping one selectively permeable membrane. It's a selectively permeable membrane, sir. It's selectively permeable. It is permeable to ions. Okay. Now, dekho, here I am introducing here on this side A side and B side. Let's take A side and B side. Okay. On A side, I'm injecting, I am putting 9 sodium molecules Here also I am just keeping 9 sodium molecules. Okay, 9 sodium here, 9 sodium here. Now tell me, sir, the sodium will move from A to B or B to A? No, it won't move from either A to B or B to A, sir. Because on both the sides, the concentration is same. Sodium concentration is same. Okay. Now, in on B side, try to understand. On B side, now I am keeping chloride molecules, 9 chloride molecules. Only on B side, I am keeping 9 chloride molecules. Okay. Now what happens? So, chloride is going to, chloride is going to do what? So, chloride, it's going to equilibrate. On this side, there is no chloride. So, chlorine will go from high concentration to low concentration. So, now equal distribution. This side, 4 chloride molecules will come. This side also, 4 chloride molecules will come. And 9 right. That 1 chloride molecule, it's getting diffuse here and there. Okay, moving here and there, sir. So equally getting distributed. Okay, but now see, I'm introducing something extra, sir. Now they go. Now what happens is the same A and B. Okay, now here. Okay, first let me show you here itself. Later, what are the changes that are occurring that I will explain. Now on this side, proteins. I'm keeping a protein. Okay, and it's having a negativity of minus 9. Okay, so 9, sir. Okay, when I kept such a protein molecule, large protein molecules, and I have kept a protein molecule. Okay, sir, these protein molecules, okay, negativity minus 9. It's an anion, sir. Okay? These are the proteins which are anions. The negative charge is minus 9 millivolts. Okay, minus 9 millivolts. So it's negative charge, minus 9 millivolts. Now, in the presence of such a large impermeable proteins, now the movement of this selectively permeable ions, the movement of these ions across the selectively permeable membrane will change that. Now, it is not going to be 9 and 9. It is not going to be 4 and 4. Now, a little change is going to occur. Do you know what is that? So, when I introduce this protein here, such a large protein molecule, in the presence of this protein molecule, now ionic balance will change. How? Now, I have kept protein here. Now, protein is which charge? Negative charge, minus 9 millivolts, for example. Okay. Now, here sodium and sodium. So, this is the negative charge, right? Protein is a negative charge. Now, as it's a negative charge, it loves to, into the A compartment, it loves to attract more positive ions. It loves to attract more positive ions. In the same way, protein is a negative charge. It will repel negative ions. It will repel the negative ions. Negativity will repel the negativity. So what happens is they go now sodium in this side. Okay, sodium in this side. Now it will become 12 instead of 9. Previously it is 9 and 9. Now this protein, which is a negative charge, it is attracting more and more positive charges. Okay, so here it is 12. 12. On this side, it is becoming how much? 6. Instead of 9 and 9, it becomes 12 and 6. Now chloride. Okay. Previously, chloride is how much? Previously, the chloride are 4 and 4. 4 and 4. And one chloride molecule is moving, dangling here and there. It's moving here and there. Now, in the presence of this protein in the A compartment, negative charges will repel the negativity. Okay, if more negative charges are going to shift into the B compartment. So here and here, you know now how much it became. Here it became 6. Previously it is 4 and 4. Okay, previously it is 4 and 4. What happened to the air server? Okay, just give me 1 minute, guys. There is some issue. Okay. Can I continue? I think it's okay now. It's okay. Uh, okay, done. So now, then what's happening, guys? Because these proteins are going to repel more negative charges inside the cell, it becomes three. In this side, there are three chloride ions instead of four chloride ions. Now it becomes three. Why? Because now these proteins are repelling more chloride to the B side. Okay. Now, then it's very simple. Okay, it's very simple now. What I have explained you in the presence of a large impermeable molecule. See, this protein is a large impermeable molecule. It is not going to be permeable. Okay, right? Okay, done. Sorry guys for the technical things. Okay, for the next 2 days it will be like this only. Like as I'm doing from the other studio, it's a little technical. It's little technical. Issues are coming. But anyway, what I'm explaining you, I'm explaining that in the presence of such a large impermeable substance, in the presence of such a large impermeable ions, the permeability, or I should say, the composition of the ions will change. So previously, how it is 9944, everything is good. But when you introduce such a impermeable ion, see this impermeable means this protein it cannot cross. Now this protein it cannot cross. Okay, so now what this protein is doing? So this protein is having an influence. Now it is showing influence in the change. Now it is showing the influence in changing this ion concentration. For example, so let's look at this now. Let's look at this now. So now previously it is 9 and 9, 4 and 4. Now it is what? Now it is here 6, here it is 12. Here it is 6, here it is just 3. Now the ionic composition changed, right? Now there is a change in the ionic composition. Okay, now there is a change in the ionic composition, sir. Now let's talk about the same whatever we have discussed in Gibbs Denon equation. So what exactly is this Gibbs-Denon equation telling us? Okay, so what exactly is this Gibbs-Denon equation telling us? Gibbs-Denon equation will give the information that the number of positive ions, look here, see, in compartment number A and in compartment number B, in compartment number A and in compartment number B, the total number of positive ions in the compartment number A should be equal to the total number of should be equal to the total number of negative ions in compartment number A. Is it true or not? Just look. Now, what is the total number of positive ions in compartment number A? In compartment number A, the total number of positive ions is 12. And what is the total number of negative ions? The total number of negative ions in compartment number A is 9 and 3. 9 and 3. Okay. So, 12 in compartment number A, 12 positive ions are there. And compartment number A, 12 negative ions are there. So, it's equal. Compartment number A is having 12 positive ions and compartment number B is having 12 negative ions. Now, the same is true for the compartment number B also. So, in compartment number B, total number of positive ions in compartment number B is equal, it should be equal to the total number of negative ions in the compartment number B. Okay, so 6 positive ions, 6 negative ions. So now tell me, sir, compartment number A, okay, compartment number A is electroneutral, right? Now compartment number A is electroneutral. The number of positive ions and the number of negative ions is same. So what is the difference? The difference is 0. The difference is 0. Okay. Now, if you look at the compartment number B, the number of positive ions and the number of negative ions are equal. So, what is the difference? 0. So, here also this is electroneutral. Compartment number A is also electroneutral. So, both these are electroneutral, sir. Okay. So, that's why there is no net diffusion of ions. What exactly the gist, what exactly I want to put into your mind is, sir, I have explained you. Sir, the composition of extracellular fluid and intracellular fluid is different. Outside there is more sodium, inside there is more potassium. Now why that sodium is not coming in? Why it is not moving? Why potassium is more inside the cell? Potassium is more inside the cell, it should go out and it should equilibrate, right? Why it is not happening? Because actually they go, look here. If you see here, now tell me, how many ions are there in the compartment number A? How many ions are there in the compartment number A? So many ions, sir. See here, 12 positive ions, 12 negative ions are there. 12 positive ions, 12 negative ions are there. 24 ions are there. Okay. Now, here, only 12 ions are there. Just 12. Here, sodium is 12. They go outside, inside. Say, for example, in compartment number A, 12 sodium ions are there. Here it is just 6 sodium ions. But still they are not moving, sir. Still they are not moving. They are in an equilibrium state. Now they are in equilibrium state. Why? Because compartment number A and compartment number B, they are both electroneutral. There is no net movement of the ions. Net movement of the ions completed. It's looking like here there is more sodium, here there is less sodium, but both the compartments are electrically neutral. Electrically neutral. So what Gibbs-Donans equation is telling us? There are 3 things which you need to know. According to Gibbs-Denon equation, the number of positive ions in the compartment number A and the number of negative ions in the compartment number A are equal. And number of positive ions in compartment number B and the number of negative ions in the compartment number B will be equal. Okay. Next, what else? The second thing, according to the Gibbs-Denon equation, so the product of sodium and chloride, the product of sodium and chloride in the compartment number A should be equal to the product of sodium and chloride in compartment number B. So what exactly is this product mean? Multiplication. In compartment number A, so 12 into 3, 12 into 3. So how much is 12 into 3, sir? 12 3 is the 36. So the product in the compartment number A and the product in the compartment number B, they are same, 36. Okay, so again, because both the compartments are electrically neutral, their voltage, see that ionic charge in the compartment number A and the compartment number B is coming, the product is coming same. So that's why there is no net movement of the ions. It is electrically neutral. Now, according to the Gibbs-Denon equation, the third important thing which you need to know is, sir, in the compartment number A, okay, look at the compartment number A. More ions are there, 12, 3, and here 9. Total number of ions, how much? Sir? So many ions are there. 12 plus 12. Okay, 12 plus 12, 24 ions are there. More ionic substances are there. More ionic molecules are there. More ions. Here, in compartment number B, less number of ions, 6 and 6. Okay, so now tell me, the osmotic tension. Okay, the osmotic tension is now different. So osmotic tension in compartment number A will be greater than compartment number B. Osmotic tension is because of what? Osmotic tension or the osmolarity is because of the ions. Now tell me where more ions are there. More ions are there in the compartment number A. Less ions are there in the compartment number B. Wherever there are more ions, there will be more osmolarity or osmotic tension will be more. So compartment number A will be having more osmotic tension when compared to the compartment number B. Okay. So what I am trying to put into your mind is, sir, according to this, okay, Gibbs Danon equation, or simply, sir, what is this Danon effect? Okay, sir, what is this Danon effect? So, Danon effect explains you in the presence of this impermeable, large impermeable substance, the ionic movements will be altered. Normally, it should be equally distributed, but in the presence of such large proteins, the ionic movements are going to be changed. Now, see, it's not equilibrium. Now it's, see, one side it is 12, the other side it is 6. Even in our cells also, that's what I told you. Even in our cells, outside sodium is more, inside less sodium is there. Inside more potassium is there, outside less sodium is there. So it looks like the number of ions inside and the number of ions outside are different, but these two are electrically neutral. Okay, so these are some important points I want you to know. At the end of the day, sir, what I want you to know is the voltage difference that is seen between the cells is called as resting membrane potential. Resting membrane potential. Now, after this resting membrane potential, let's discuss about the action potential in a neuron. Okay, action potential in a neuron. Okay, action potential in a neuron. Sir. Look here, guys. Dekho, this is one neuron. Imagine this is a one neuron. Sir. Okay. Now you know the parts of the neuron, right? First, let me explain you the parts of the neuron. Look, this is the cell body. Okay, this is the cell body. This is the axon. And what is this? This is the nerve terminal. This is the nucleus. These are the dendrites. Okay, these are the dendrites. Now, you know, right? The axons are surrounded by myelin sheath. This is called as the myelin sheath. Okay, this side also it will be there. So it's a myelination, sir. Myelination around the neurons. Myelin sheath is going to be there. Now, this region is called as axon hillock. This region is called as axon hillock. So that region is called as axon hillock. Now, what is the importance of this axon hillock is that's the place where action potentials are generated. Okay, the action potentials are generated in the axon hillock. Now, the nerves, when they are resting, okay, now when the nerves are resting, they are having a resting membrane potential of every cell will having a resting membrane potential, sir. Each and every cell will have a resting membrane potential. I have explained you why resting membrane potential, because of the differential concentration of the ions. Okay, differential concentration will be there. Okay, more potassium is going out of the cell. As the more potassium is going out of the cell, that will contribute to the electronegativity inside the cell. Sodium potassium ATPases. Less potassium is coming into the cell, more sodium is going out of the cell. So because of this, there can be negative resting membrane potential. In the same way, our neurons will also have resting membrane potential of how much? Minus 70 millivolts. Minus 70 millivolts. Okay, so resting membrane potential of a neuron, this is the MCQ which was asked, it's a 70 millivolts. Now, let's see how action potential is generated. How action potential is generated, sir. Okay, now what is that action potential? That I will explain you now. Okay, look here, guys. Imagine this is your axon. Okay, axon. This is the axon of a neuron. Okay, this is the axon of the neuron. Now, outside, what is this? Sir, this is the myelin sheath. Here it is a myelin sheath present. Here there is another myelin sheath. Here other myelin sheath, like continuously. They're all the myelin sheaths. Okay. Now tell me, what is the resting membrane potential? The resting membrane potential is minus 70 millivolts. Okay, minus 70 millivolts. Now, see, when you stimulate this neuron, okay, when you stimulate this neuron, now let me put a graph first. Look here, I am plotting a graph, sir. Okay, I am plotting a graph. Now here I am showing you the voltage minus 70 millivolts. Okay, this is minus 70 millivolts. Now, what you are doing is, you are stimulating that neuron, sir. You are stimulating that neuron. If the stimulation, whatever you are giving, if it is powerful enough, okay, you are giving the stimulations. Okay, you are stimulating the neuron. So, from minus 70, the voltage is going to, now for example, minus 60. Nothing will happen. If you are giving the stimulation from minus 70, it is going to minus 65. You are stimulating the neurons. Nothing will happen. But if the stimulation is powerful enough, which means now from minus 70 millivolt, now it is going to minus 55 millivolts. Minus 55 millivolts. So resting membrane potential from minus 70 is gone to minus 55. Okay, so initially how much is it? It's minus 70. Okay, let's put it this way. It's always at minus 70. Now you are giving little stimulation. It gone up, again it come back. You gave a little more stimulation. It have gone up and it have come back. These are failed initiations. Failed initiations. But when you give powerful stimulation, when a powerful stimulation is coming to a neuron, you know what happens? Now from minus 70, it is going to minus 55. Now this minus 55, this is called as threshold potential. Okay, it is called as what? It is called as a threshold potential, sir. Now that is the minimum potential required for depolarization. Okay, now you gave a stimulation from resting membrane potential, it gone to threshold potential. Do you know what happens now in this neuron? So there goes, sir. Now you are giving stimulation. Okay, is what happened. Accept. It's everything okay, right? But there is an issue. Let me see in the YouTube. Okay, everything is okay. No, okay, everything is okay. Now they go. Now you are giving stimulation. Now you are giving the stimulation, sir. Okay. Now when you are giving the stimulation, okay, when you are giving the stimulation, now from minus 70, it came to minus 55 millivolts. Okay, now it came to minus 55 millivolts. Now do you know what happens? Sir, on this neuron, your neurons are made in such a way. On your neurons, sir, there are voltage gated. Okay, there are voltage gated sodium channels present. Voltage gated sodium channels. What does it mean by voltage gated? They are sensitive to voltage. Whenever minus 55 millivolts, when it is attained, do you know what happens? Now, these sodium channels, they will start to open, sir. Okay, now the sodium channels, now they are open. Now the sodium channels, now they are open. Previously they are closed. Now whenever this threshold potential is attained, now the sodium channels are open. Now from outside, from outside which concentration is more? There is more sodium outside the cell. There is more sodium concentration outside the cell. Now the sodium, it will start to come into the cell. Now sodium is coming into the cell. Now tell me what happens, sir? Because of influx of the sodium, lots and lots of sodium will come into the cell, sir. Now, lots and lots of sodium is coming into the cell. So what happened to the membrane voltage? Now previously it is minus 70. From minus 70 it have gone to minus 55. So when minus 55 is attained, voltage gated sodium channels are opened. So lots and lots of sodium start to come into the cell. So because of the sodium, what happens? Sir, the cell voltage will become positive. Okay, now it's becoming plus 50 millivolts. Now the cell is getting depolarized, activated. Now inside the cell, the voltage is getting into positivity. Now the resting membrane potential, from resting membrane potential, now you have gone to first threshold potential, from threshold potential depolarization, sir. Now inside the cell, lot of sodium came into the cell. So this stage is called as depolarization. So what is the stage called as? This is called as depolarization. This is called as depolarization. And the depolarization is because of what? So the depolarization is because of influx of sodium ions. Okay, there is influx of sodium ions. Sodium influx. Due to influx of sodium ions, depolarization is occurring. Now you need to understand. Now you need to understand how, sir, the action potential is going to, how it is going to travel in the nerves, how this electricity is going to travel in the nerves. Alright guys, tell me what exactly is action potential, what exactly is this nerve impulse, or what exactly is electricity? Electricity is a flow of ions, right? Electricity is nothing but the flow of ions, positive ions, flow of the ions, sir. So what exactly happens is, they go, now you need to see, sir, lot of sodium came into this. Okay, now some sodium ions are going to move to this side. Now here the resting membrane potential is minus 70 millivolts in this area, in the surrounding area. Now the sodium ions, some sodium ions, it will come to the surrounding area. Now from, due to the movement of the sodium ions, tell me what happens. Due to the movement of the sodium ions, what happens? Sir, from here in this area, from minus 70, it will become minus 55 millivolts. Whenever this voltage is attained, minus 55 millivolts is attained. Now what happens? Sir, immediately in this area, voltage gated sodium channels will start to open. Voltage gated sodium channel opens, sir. So immediately here also, lot of sodium came into the cell. Now see, they go. What is happening? The positive ions are flowing. Okay, now the sodium came. Now bringing minus 55 to plus 15 millivolts. That is depolarization. The sodium came into the cell, leading to depolarization. Now, what this sodium will do? Sir, here in this area, resting membrane potential is minus 70 millivolts. Now, some sodium will come to this surrounding area, bringing this minus 70 millivolts to minus 55 millivolts. Okay, minus 55 millivolts. So, from resting membrane potential, threshold potential is attained. When the threshold potential is attained, what happened to the voltage gated sodium channels in this part of the neuron? They are open. Now again sodium comes into the cell. So this is how a nerve impulse is propagated. Action potentials are getting propagated, sir. It is nothing but electricity. Okay, just like electricity, sir. So it's the flow of ions. Sodium comes into the cell. The sodium will go into the surrounding area, bringing the resting membrane potential to the threshold potential. Once threshold potential is attained, more sodium will come into the cell. That sodium will go again to the next area, making depolarization, going to the surrounding area, making depolarization. So this is how the nerve impulse is going to be conducted along the neurons. Okay, now look, what you should know is, sir, in this area, okay, sodium came into the cell, depolarization occurred. Now the cell become depolarized. It should not be depolarized continuously, right? It should not be depolarized continuously. This area become depolarized. Okay, but what should happen to this area now? So that area have to go back to normal. That area have to go back to normal, sir. Now, once plus 50 is attained, do you know what happens? Now, in this part, what happens is the potassium channels will open, sir. Voltage gated potassium channels will open. What is voltage gated potassium channels are doing? Inside the cell, more potassium is there. Now, potassium will start to go out. Okay, potassium will start to go out. As the potassium is going out of the cell, positive charges are going out of the cell. Again, this plus 50 will go back to minus 70 again. The plus 50 will go back to minus 70 again, sir. So the same thing, look here. In this graph, I will explain you. So depolarization occurred, completed. Sir, after depolarization, what will happen? Sir, once depolarization is completed, now repolarization should occur. Okay, repolarization should occur. So what happens is, now potassium channels are opened. Now potassium will start to go out of the cell. As the potassium is going out of the cell, positive charges are going out of the cell. The cell voltage will come down again. It will come down, sir. It will come down. So this phase is called as repolarization. Okay. So initially there will be depolarization due to sodium influx, and there will be repolarization due to potassium efflux. Okay, so depolarization is due to sodium influx. Okay, depolarization is due to sodium influx, and repolarization is due to potassium efflux. Do you know what happens? So sometimes more potassium will go out of the cell. Okay, more and more potassium is going out of the cell. When more and more potassium, continuously potassium is going out of the cell. When potassium is going out of the cell, what happens? Even the membrane potential will go to minus 90, not just minus 70, it is going to minus 90. So what is this is called as? This is called as hyperpolarization. The cell is getting more and more inactivated. So this is called as hyperpolarization. The cell is becoming hyperpolarized. More potassium is going out of the cell. The cell is becoming more electrically negative. Hyperpolarization. We will call it as hyperpolarization. But at the end of the day, because of sodium potassium ATPases, at the end of the day, the membrane potential will be brought back to normal. Okay, it will come back to normal cell. So how many phases are there? This is resting membrane potential. Okay, this is resting membrane potential. This is threshold potential, movement to the threshold potential minus 55. Later there is depolarization followed by repolarization, and there will be hyperpolarization. Again coming back to what? Again coming back to resting membrane potential. So coming back to resting membrane potential. Okay. Now, sir, this phase which I am showing you. Okay, this phase which I am showing you from here to here. What is this? Oscillation of the resting membrane potential from minus 70 to minus 55. Minus 70 to minus 55. This is called as phase 1. This is called as what? This is called as phase 1, sir. Okay, phase 1. Now, right, how many phases are there in the action potential of a neuron? First, right, phase 1. Phase 1 from where to where? From minus 70 millivolts to minus 55 millivolts. Okay, minus 55 millivolts, sir. Okay, resting membrane potential to threshold potential. This is called as a phase 1. Now, after phase 1, what do we have from here to here? From here till here. What is the depolarization? So, that is called as phase 2. Phase 2. That is depolarization. Okay, next, after depolarization, from here, okay, till here, repolarization. Phase 3, that is called as phase 3. Phase 3 is repolarization, sir. Okay, phase 3 is repolarization. Next, after repolarization, what do we have? From here to here. Okay, see the membrane potential is becoming more negative, more negative. So that is called as phase 4. That is hyperpolarization. 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 After hyperpolarization, what is happening? Again, coming back to resting membrane potential. So that is called as phase 5. Phase 5 is RMP, resting membrane potential. So these are the 5 phases in the action potential of a neuron. Alright guys, what I am telling you is, sir, there is this one neuron, simple, one neuron. When you stimulate, actually it is having resting membrane potential at minus 70. It is sleeping. No activity, no flow of charges, no electrical impulses. It is simply sleeping. When you stimulate it, okay, when you stimulate it, for here also neurons will be there. No? When you give enough stimulus, when you give enough stimulus, the resting membrane potential reaches the threshold potential. Once the threshold potential is attained, automatically depolarization will occur. Okay, automatically depolarization will occur. After depolarization, that area will become again repolarized. During depolarization, sodium comes into the cell. The sodium will go to the surrounding area. The sodium will go to the surrounding area, makes the surrounding area to undergo depolarization again. More sodium comes in. Now the sodium will go to the surrounding area, depolarization. Surrounding area, depolarization. So depolarization continues. So there will be a wave of depolarization. There will be a wave of depolarization followed by repolarization. First, this area is undergoing depolarization. Now this area will help in the depolarization of the surrounding area. When the surrounding area is getting depolarized, the first area will undergo repolarization. Okay, so what I'm trying to put into your mind is, they go, sir, simple. Now this is a neuron. Okay, now let's divide it into three parts. Three parts. Now, first here minus 70 millivolts. Now you have stimulated it. From 70 millivolts, it becomes minus 55 millivolts. So threshold potential is attained. Threshold potential is attained. Now, what happens? Now, what happens is, here sodium channels, voltage gated sodium channels are going to open. These are the voltage gated sodium channels, sir. They are open. Now, sodium comes into the cell. Sodium is coming into the cell. Okay. Now, this sodium, what it will do? Sir, because of this sodium, it is becoming plus 50 millivolts. Lots and lots of sodium is coming into the cell. Tons and tons of sodium is going to come into the cell. So, it becomes plus 50. Now, this region have undergone depolarization. Okay, depolarization. Activated, depolarized. Become positive. Membrane become positive, sir. Voltage become positive. Okay. Now, this sodium, it will go to the surrounding area. It will go into the surrounding area. Now, here it is minus 70. Now, due to the movement of the sodium, from minus 70, it will become minus 55. Okay. So now in this area, voltage gated sodium channels will open, sodium will come into the cell. But look, during this area that is undergoing depolarization, now here depolarization is occurring, sir. But what happened in the first area? Now in the first area, now in this area, the voltage gated potassium channels are opened. Potassium will start to go out of the cell, leading to repolarization. Now here there is repolarization. Repolarization have started here. Repolarization. So when this area is undergoing depolarization, here it will undergo repolarization. So same thing. Depolarization, this area repolarization. Depolarization, repolarization. Depolarization, repolarization. So a wave of depolarization followed by a wave of repolarization. Depolarization, repolarization. Depolarization, repolarization. So this is called as action potential. In an action potential, first an area will undergo depolarization followed by repolarization. The other area also becomes first depolarization, that area will undergo repolarization. So this is called as action potentials. This is how the ions are going to flow inside the neurons. You can say the electrical impulses are getting transmitted in the neurons. Now, what you need to know as a doctor? What you need to know as a doctor? There goes, sir. Now, have you ever heard about like an anesthesia? What anesthetic agents? Now, imagine I have applied anesthetic agents here, sir. I have applied anesthetic agent here. One anesthetic agent called as a lidocaine. Now, what this lidocaine is going to do, So, this anesthetic agent, lidocaine, is going to block the sodium channels. Anesthetic agents. Okay, anesthetic agents. Example, lidocaine. Lidocaine. What they will do? They will block voltage gated sodium channels. Okay, voltage gated sodium channels. When the voltage gated sodium channels are blocked, okay, when the voltage gated sodium channels are blocked, do you know what happens? Sir, do you think now sodium will come into the cell? No. So do you think depolarization will occur? No. When there is no depolarization, there is no repolarization. So the nerve impulses are getting conducted, action potentials are getting transmitted across the neuron. No. So same here, you have applied the anesthetic agents. So here in this area, the neurons on the neurons, the voltage gated sodium channels are inhibited. So how much ever you stimulate, they do not produce the action potentials. Why? Because the sodium channels are blocked, the neurons are not getting depolarized. So that's how anesthetic agents work, sir. So anesthesia, how it works, it blocks the voltage gated sodium channels. So sodium cannot go into the cells. So the neurons cannot undergo depolarization. When the neurons are not getting depolarization, the impulses are not transmitted to the central nervous system. The action potentials are not traveling across the neurons. So the information is not going to the central nervous system. You cannot feel anything. Whatever you do here, you cannot feel anything because the neurons are inhibited. The sodium channels are inhibited with the help of this drug called as lidocaine. Okay, done, sir. Now, after this, what else you need to know? Simple things. Dekho, let me draw here. Look here, guys. Sir, what is this? First, minus 70 millivolts. Here it is minus 55 millivolts. Okay. Now, look at this. This is resting membrane potential. These are phase 1. This is the phase 1. Okay, this is the phase 1. Now, later what do you have? Depolarization followed by repolarization, and little hyperpolarization will be there. Again back to normal resting membrane potential. Okay, depolarization, repolarization. This is hyperpolarization, coming back to resting membrane potential. Okay, now these are the phases, right? These are the phases. Now, see, there is this phase from here, sir. See, from here. Okay, let me write from here till here, sir. Okay, so this period which I am showing you, from where to where? From the starting, sir. From here, starting. Okay, starting of the action potential, phase 1, starting of the phase 1 till to one third of repolarization, one third of the repolarization, sir. Okay, actually I should keep it here. Just let me make a small change. For example, to here. Let's put it this way. So this period is there, right? This period which I am highlighting. So during this period, from here till to here. Okay, so during that period of the neuron, depolarization completed, now repolarizing. The depolarization completed, sir. Okay, depolarization completed. Now repolarizing. This part is getting repolarized. This part is getting repolarized. Now, if you stimulate that neuron again, do you think one more action potential is going to be generated? Now you are giving stimulation. Now again one more action potential is going to be generated. No, no. How much ever you stimulate it during this period, which I have shown. So this period is called as absolute. Okay, this is from here to here. So the pink area which I have shown. This is called as absolute refractory period. This is called as absolute refractory period. So what exactly is absolute refractory period? Absolute refractory period means how much ever the stimulus you give. Okay, 1,000 times, 10,000 times than the normal stimulus. There is no production of action potential. No new action potentials are produced. No new action potentials. No new action potentials are produced during absolute refractory period. When a neuron, when it is in absolute refractory period, how much ever you stimulate it, no new action potential is generated. But now from here to here, what is this period? Now here the neuron, it is repolarizing and hyperpolarizing. Okay, now during this period, okay, now the neuron is hyperpolarizing, so repolarizing and hyperpolarizing, the last part of repolarization, last two-thirds of the repolarization. Now during this period, if you give any action potential, sorry, not action potential, if you give any stimulus, new action potential is generated. Yes, there is a possibility of generation of new action potential. Yes, a new action potential can be generated, but with not normal stimulus. You need to give higher stimulus. If you give higher stimulus than normal, if you give higher stimulus than normal, yes, there is a possibility of development of one more action potential. There is a possibility of development of one more action potential from here. Okay, so this period which I have shown here, this is called as a relative refractory period. Okay, relative refractory period. Now, what exactly is relative refractory period? Let me write. Giving higher stimulus. Okay, giving higher stimulus. What it will do? Giving higher stimulus. Yes, there is a possibility for the generation of new action potential. A new action potential can be generated. So, these two important things which are needed: absolute refractory period, no generation of any action potential, and relative refractory period. In relative refractory period, yes, you can generate an action potential. You can generate an action potential. So what you need to know, okay, the basic thing what you need to know is, sir, every cell is having a resting membrane potential. Okay, every cell will be having the resting membrane potential. Here they go, this image what we are seeing, see, this is the voltmeter, sir. With the help of this voltmeter, I am putting one electrode into the cell. I am keeping one electrode outside the cell. Sorry, I'm keeping one electrode outside the cell. I'm keeping one electrode inside the cell, and I'm measuring the voltage difference. Okay, I'm measuring the voltage difference. Each and every cell will have a different voltages. Each, okay, different types of cells have different resting membrane potentials. Now, why there is this resting membrane potential? Why there is this difference? Why there is this negativity inside the cell? I have explained you the reasons. The reasons are, sir, the cells are made in such a way that outside the cell different types of ions are there, inside the cell different types of ions are there. Not only the types of ions are different, different concentration of ions will be there. Outside more sodium is there, more chloride is there, more calcium is there, inside more potassium is there, and more anions are there. Difference in the composition of the ions that can contribute to the resting membrane potential. And the membrane is selectively permeable to different types of ions. Most of our membranes are having this leaky potassium channels. More potassium is going out of the cell. As more potassium positive charges are going out of the cell, now inside the cells there will be more negativity. And not only that, sir, our cells are having these pumps called as sodium potassium ATPases. The sodium potassium ATPases throws 3 sodium out of the cell, brings only 2 potassium into the cell. More positive charges are going out, but only less positive charges are coming in. So because of that, yes, there is a possibility of difference in the voltage. Okay, so this is also completed. All these are responsible for resting membrane potential. Now what else, sir? Now in this Danon's effect, what I have explained is, in Danon's effect, simple Danon's effect is what? Danon's effect is in the presence of large impermeable molecules like proteins. In our cells, proteins are there, sir. In our cells, these proteins are there. Because of the presence of such large impermeable molecules, they will create this. See, now what they are creating? Now they are creating this ionic imbalance. Now inside compartment number A, more ions are there. Outside the compartment number B, less ions are there. Even because of this, there is a chance that there will be development of resting membrane potential because of this differential ions, like ionic compositions. Okay, so these are the points. After this, I have explained you the action potential. Okay, what are the phases of the action potential? Phase 1, 2, 3, 4, and 5. Okay, the depolarization is due to sodium, repolarization is due to potassium, and more potassium is going out of the cell, that will cause hyperpolarization. Okay, so these are the 5 phases of the action potential. And if you give anesthetic agents like lidocaine, what they will do? They will block the voltage gated sodium channels. If the voltage gated sodium channels are blocked, do you think action potentials can be generated? No action potentials can be generated. And last one, what are the 2 refractory periods that you should know? Absolute refractory period, the first part, and the relative refractory period. During absolute refractory period, you can generate one more action potential. During relative refractory period, you cannot generate any action potential. No new action potentials can be generated. Okay, so with this the topic is completed. With this the topic is completed, sir. Okay, in tomorrow's class we will do the muscle physiology. Okay, now physiology is little boring topic, but muscle physiology, how muscle contracts, very very important. That we will integrate with the medicine also, like as a doctor, different disorders, different diseases I will teach you. Okay, see nerves in normal regular classes, when you attend the the university classes, then you will understand it better, sir. Okay, that gives Garon equation, Garon gives Garon equation, that you will understand better. Okay, in university you will have a lot of time, so we can do it little by little. Okay, little by little we can form the concepts. Now if you have all the concepts at a time, it will be little tough for you to understand. But anyway, now from tomorrow we'll do the muscle physiology. Muscle physiology, how muscle is going to contract, how the muscle, what is the structure of the muscle. Okay, muscle fascicles, myofibrils, myofilaments. Okay, the muscle contraction, sliding filament theory. Okay, that we will discuss in the tomorrow's class. Okay, this will be enough for today. In tomorrow's class, let's see the muscle physiology. Okay guys, hope the video is helpful. Thank you. See you tomorrow.